Hello everyone, my name is Kodai Wada. I work at Kobe University in Japan. I would like to thank the organizers for inviting me to speak at CKVK seminar. In this talk, we give a classification of string links up to 2n-moves and link-homotopy by using Milnor invariants. This classification tells us a relation between 2n-moves and Milnor invariants. This is a joint work with Haruko Miyazawa and A.K.A. Yasara. Let's get started. First, we mention the motivation of this work. Let n be a positive integer. A 2n-move is a local move as shown here. This move replaces two parallel strands with 2.5 and vice versa. The 2n-moves were probably first studied by Kinoshita in 1957. Since then, 2n-moves have been well studied in knot theory. We remark that a 2-move is equivalent to a crossing change. That is, a 2-move can be accomplished by crossing changes and isotopies. On the other hand, a crossing change can be accomplished by 2 moves and isotopies. In this sense, a 2n-move is a generalization of a crossing change. Here we introduce one equivalence relation. We say that two rings L and L prime are 2n equivalent, denoted by this, if they are related by a sequence of 2n-moves and isotopies. In the study of 2n equivalence, the relations to link invariants are well studied. The focal fact is that the linking number modulo n and the Fox 2n coloring are invariant under 2n equivalence. In 1980, Kinoshita proved that if two rings are 2n equivalent, then their one-variable Alexander polynomials are congruent modulo the ideal generated by two polynomials n times 1 minus t and 1 minus t times 1 plus t squared plus t to the power of 4 plus plus t to the power of 2n plus 2. Such a relation is given for each of the Jones, Kaufman, and Humphreys-Petty polynomials by Pistetsky in 1988. As mentioned above, the relations between 2n equivalence and link invariants are increasingly well understood. In this talk, we discuss a relation between 2n equivalence and Milnor invariants. In the 1950s, John Milnor defined family of invariants for rings called Milnor mu-bar invariants. for a link L and for a sequence I, we can define an integer mu Li. This integer is called the Milnor number of L. Unfortunately, this integer is not an invariant of L. So we consider a non-negative integer delta Li, which is determined by Milnor numbers. Then the residual class of the Milnor number mu Li modulo delta Li is an invariant of L. This residual class is denoted by mu bar Li. This is the mu bar invariant. In 1990, Habega and Lin defined Milnor numbers for string rings and proved that these numbers are invariants of string rings. They are called Milnor mu invariants. There are various geometric equivalence relations on rings over string rings, which are related to Milnor invariants. For example, link-homotopy, concordance, and CK equivalence. Both Milnor invariants and 2n equivalence are well studied in knot theory. However, there are no results connecting Milnor invariants and 2n equivalence. This is the motivation to study a relation between Milnor invariants and 2n equivalence. In this work, we gave such a relation. So the purpose of this talk is to describe the relation between two Milnor invariants and 2n equivalence. In this talk, we will mainly focus on Milnor mu invariants of string rings. So we recall the definitions of string rings and their mu invariants. Let I1 that Ik be k copies of the unit interval 0, 1. Let D be the unit 2 disk equipped with k points x1 that are xk. In particular, we choose these k points to lie in order on the x-axis, like this, x1, x2, that are xk. Roughly speaking, a string ring is a pure braid without monotone condition. More precisely, a k-component string ring is the image of a proper embedding of the disjoint union of k copies of the unit interval 0, 1 into d times the unit interval, such that the image of each I sub I runs from the point xi0 to the point xi1. This figure shows an example of a three-component string ring. The first strand runs from x10 to x11. The second strand runs from x20 to x21. And the third strand runs from x30 to x3 1. We denote by 1k this k-component string link, which is shown here. And we call 1k the trivial k-component string link. This is the definition of string links. In order to define mu invariants, we consider meridians and longitudes. Let sigma be a k-component string link. We denote by z of sigma the fundamental group of the complement of the string link sigma with respect to a base point b, which is on the boundary of d times 0, like this. Let mi be the ith meridian of sigma. This loop represents the ith meridian my. Let Ly be the ith longitude of sigma. This loop represents Ly. In this talk, we assume that each longitude Li is the preferred longitude. That is, we assume that this red part is the zero-framed parallel copy of the ith component of sigma. Here we introduce two notations, gamma qz and f of m1 dot mk. Let q be a positive integer. We denote by gamma qz the qth term of the lower centered series of a group z. That is, gamma 1z is equal to the original group z, and gamma q plus 1z is the commutator subgroup of z and gamma qz. We also denote by f of m1 dot mk the free group on the set m1 to mk. It is known that the q's nilpotent quotient of the group of the string link sigma is isomorphic to the q's nilpotent quotient of the free group F. Therefore, by this theorem, each longitude Ly can be expressed modulo gamma qz of sigma as a word in k meridians of sigma m1 dot mk. We denote this word by lambda iq. Mu invariants are obtained from the information of this word lambda iq. To catch the information of lambda iq, we consider the Magnus expansion E of lambda iq. The Magnus expansion E is a homomorphism from the free group of rank k into the ring of formal power series in non-commutable variables x1 that are xk with integer coefficients, defined by sending my to 1 plus xi and sending my inverse to 1 minus xi plus xi squared minus xi cubed plus da da da. Now we can give the definition of the mu invariant of sigma. Let large I be a sequence j1 small j1 that small js small I of indices in the set of 1 to k, where s is less than q. We define mu sigma I as the coefficient of the monomial xj1 that xjs in the Magnus expansion of the word lambda iq. We emphasize that in the sequence large I, the last index small I and the other indices play different roles. The last index small I specifies the word lambda iq. In this Magnus expansion, the other indices j1 js specify the monomial xj1 xjs. This is the definition of the Milner mu invariant of sigma. This mu invariant is related to 2n equivalence like this. Let n be a positive integer. If two string rings are 2n equivalent, then their mu invariants are congruent modulo n for any non-repeated sequence. Also, let p be a prime number. If two string rings are 2p equivalent, then their mu invariants are congruent modulo p for any sequence I of length less than or equal to p. We note that in the second assertion, this sequence may have repeated indices. For the second assertion, we have two remarks. One is that the restriction on the length for sequences must be necessary. For example, let sigma 1 be this two-component string link. This is for equivalent to the trivial two-component string link. On the other hand, the mu invariant of sigma 1 for the sequence 1, 1, 2 is equal to 1, which is not congruent to 0 modulo 2. The other remark is that the second assertion cannot be extended to the 2n equivalence classes of string links for a non-prime number n. For example, let sigma 2 be this two-component string link. It is 8 equivalent to the trivial two-component string link. On the other hand, the mu invariant of sigma 2 for the sequence 2, 1, 1 is equal to 10, which is not congruent to 0 modulo 4. Okay, these are two remarks. We turn to the first assumption. By this assertion, we see that if there exists a non-repeated sequence I such that mu invariants of sigma and sigma prime for this sequence I are not equal, then there exists a positive integer such that sigma and sigma prime are not 2n equivalent. By contraposition, if sigma and sigma prime are 2n equivalent for any n, then they have the same mu invariant for any non-repeated sequence I. This observation gives an interesting result. We will explain such a result in the next slide. This remark is the same one as in the previous page. Here we introduce link-homotopy. We say that two string links sigma and sigma prime are link-homotopic, denoted by this, if they are related by a sequence of self-crossing changes and isotopies. A self-crossing change is a crossing change involving two strands of a single component. In 1990, Habiga and Link proved that two string links are link-homotopic if and only if they have the same mu invariant for any non-repeated sequence. This Habiga-Linz classification and this observation gives the following proposition. If two string links are 2n equivalent for any n, then they are link-homotopic. Therefore, the set of 2n equivalence classes of a string link sigma determines the link-homotopy class of sigma. I think this is an interesting consequence of our result. Next, we mention our main result of this talk. Recall that if two string links are 2n equivalent, then their mu invariants are congruent modulo n for any non-repeated sequence. From this proposition, we may consider whether the converse is true or not. The answer is that the converse is not true. However, the converse holds for a weaker equivalence relation than 2n equivalence. Like this. We say that two string links sigma and sigma prime are 2n plus LH equivalents, denoted by this, if they are related by a sequence of 2n-moves, self-crossing changes, and isotopies. The term 2n plus LH stands for the combination of 2n equivalence and link-homotopy. This is the main result of this talk. Two string links are 2n plus LH equivalent if and only if their mu invariants are congruent modulo n for any non-repeated sequence. The direction from left to right follows from link-homotopy invariance of mu invariants indexed by non-repeated sequences and the proportion above this. On the other hand, to prove the converse direction from right to left, we give a normal form of a string link up to 2n plus LH equivalence. We will explain this normal form. Let I be an integer between 2 and k. Consider an injection pi from the set of 1 I into that of 1 to k such that pi of j is less than pi of I minus 1, sorry, and it is less than pi of I, where j is an integer between 1 and I minus 2. We denote by f sub I the set of such injections pi. We remark that the cardinality of this set fi is equal to the factorial I minus 2 times the binomial coefficient ki. For an injection in fi, we define b pi as a bound sum of the trivial k component string ring and the ith component middle link. See this figure. The bounds are complicated in general. Okay. We also define, so we note that b pi is a k component string link. Okay. We also define b pi inverse as b pi with a half cis on a band, say this band, like this. Okay. Under this setting, in 2009, Yasuhara constructed a normal form of a string link up to link-homotopy. Using this normal form, Yasuhara gave an alternative proof for the link-homotopy classification of string links due to Haben and Lin. We give the detail of this normal form. Let sigma be a k component string link. Then sigma is link homotopy to the stacking product sigma 1, sigma 2, sigma k minus 1. Here, for two string links sigma and sigma prime, the stacking product of them represents this string link. Okay, we go back to the statement. For each I, sigma I is a k component string link of this form. More precisely, the stacking products of b pi to the power of x pi. The stacking product runs over all injections pi in fi plus 1. And where the exponent x pi is this integer. The important fact is that x pi is determined by mu invariant of sigma. Therefore, each sigma I is determined by mu invariant of sigma. Hence, this normal form is determined by mu invariant of sigma. Based on this result, we give a normal form of a string link up to 2n plus LH equivalence. To do so, we need the following lemma. This key lemma states that the k-component string link b pi to the power of n over minus n is 2n plus LH equivalent to the trivial k-component string link for any pi or any injection pi in Fi plus 1. Applying this lemma to Yasara's normal form, we have the following proposition. Let sigma be a k-component string link. Then this sigma is 2n plus LH equivalent to the stacking product of tau 1, tau 2, tau k minus 1. For each I, tau I is the k-component string link of this form. More precisely, the stacking product of b pi to the power of y pi. We note that the difference of tau I and sigma I in Yasara's normal form is the exponent of b pi, this and this. And where the exponent y pi is a non-negative integer, which is less than x pi, such that y pi is congruent to x pi modulo n. The important fact is that this integer y pi is determined by mu invariance modulo n of sigma, because x pi is determined by mu invariance of sigma. Therefore, this normal form is determined by mu invariance modulo n of given string link sigma. So using this proposition, we can prove the direction from right to left of the main theorem. Moreover, by this proposition, we can understand an algebraic structure of k-component string links up to 2n plus LH equivalence. We denote by SL of k the set of k-component string links. This set has a monoid structure under stacking product star and with a trivial k-component string link 1k as a unit element. Havega and Lin prove that the set of link-homotopy classes of SLK forms a group, and it has rank R of k, which is the sum of the factorial of I minus 2 times the binomial coefficient ki. Using this result and lemma and the lemma and the proportion in the previous page, we have the following theorem. The set of 2n plus LH equivalence classes of SLK forms a finite group generated by elements order n. So this group has a torsion. Moreover, the order of this group is equal to n to the power of R of k. Okay, let's go to the final section. In the previous sections, we have studied validated string links. Now we address the case of links. for a k-component string link sigma, its closure sigma hat is a k-component link in the 3-sphere, obtained from sigma by connecting the endpoints of each strand with an arc, like this. We note that every link can be represented by the closure of some string link. Here we define a non-negative integer delta sigma I, which is defined, we define delta sigma I as the greatest common divisor of all mu sigma j, such that the sequence j is obtained from I by removing at least one index and permuting the remaining indices cyclically. And then the following theorem is known. Let L be a link, and let sigma be a string link whose closure represents L. Then the original Milner mu bar invariant of the link L coincide with the residual class of mu sigma I modulo delta sigma I. This theorem means Milner link invariants can be obtained from Milner string link invariants. Here we introduce two new invariants of links. Let L be a link, and let sigma be a string link whose closure represents L. We define delta NL of I as the greatest common divisor of mu delta sigma I and N. We also define mu bar NL of I as a residual class of mu sigma I modulo delta NL of I. By the theorem in the previous page, these numbers are invariants of the link L. We call this invariant the delta N invariant of L. We also call this the mu bar N invariant. For these link invariants, we have the following proposition. This is a link version of the invariance of Milner invariance under 2n equivalence. Let n be a positive integer. Two links are 2n equivalent. Then they have the same delta n and mu bar n invariance for any non-repeated sequence. Also, let p be a prime number. If two links are 2p equivalent, then they have the same delta p and mu bar p invariance for any sequence I of length less than or equal to p. Moreover, we have the following classification result of links. Let L and L prime be k-component links such that their delta n invariants are equivalent to n for any non-repeated sequence I of length k. Then L and M prime are 2n plus LH equivalent if and only if they have the same their mu bar n invariant for any non-repeated sequence I of length k. as a direct corollary, we have the following. Let L be a k-component link, and let T be the trivial k-component link. L and T are 2n plus LH equivalent if and only if the delta n invariant of L is equal to n, and mu bar invariant of L is equal to 0 for any non-repeated sequence I of length k. In the general case, we need a certain assumption to classify links up to 2n plus LH equivalence. On the other hand, delta n and mu bar n invariants are sharp enough to detect trivial links up to this equivalence relation. Okay, finally, we give one comment concerning a validated extension of our main classification result of string links. Consider a validated string link, which is a diagrammatic extension of a classical string link in the 3-ball. In 2017, Odu, Berengeri, Mayo, and Wagner defined Milner invariants denoted by mu w for validated string links, and proved that mu w invariants for non-repeated sequences classify validated string links up to SB equivalence. This equivalence relation is generated by this local move called a self-crunching visualization. Using mu w invariance and SV equivalence, our classification result of classical string links can be extended to validated links like this. Two k-component validated string links, sigma and sigma prime, are 2n plus SV equivalent if and only if their mu w invariants are congruent modulo n for any non-repeated sequence I, and sigma and sigma prime have the same difference mu w of ij minus mu w ji for any j and I. Here, 2n plus SV equivalence is the combination of 2n equivalence and SV equivalence. Okay, that's all for my talk. Thank you for watching.